provide to me a mathematical definition. What do you mean? It's difficult to express it. Of course, we have had some statisticians that tried to provide definitions. So let's now go into this definition of probability. Keep in mind that the purpose at the end is produce a synthetic series. But of course, if you knew how much likely, what is the probability of this numbers in the series to occur, what is the probability for the river flow to be high and to be low, then when you know the probability, then you can generate a synthetic series. If you knew the probability for sure, like in May for sure I know that river flows have this probability, so 10 cubic meters per second is 5%, 15 cubic meters per second is 15%, etc. Then if you knew these probabilities for every month, every period, with full details, then you can generate a synthetic series. So keep in mind that the definition of probability of river flow, quantitative definition, would allow us to solve the problem. So it's important that we try to give a definition of probability, mathematical definition. Let's think, for instance, at the annual maximum river flow. If I could say that I have a probability of 10% that the annual maximum river flow is greater than 100 cubic meters per second, I have solved many of my design problems. So probability is really relevant. So let's provide the definition. There are two categories of two definitions for probability. And please pay attention to this, because it helps you a lot to understand these two definitions to get oriented in the terminology and to get oriented in this topic. Let me start from the second. It is more immediate to explain, which is the Bayesian definition of probability. Very often you hear about this term, even in engineering. So Bayesian approach, Bayesian theory, etc. It has to do with probability and therefore with statistics. And let's define it in this way. Bayesians, which means statisticians that like the Bayesian method, assign probability to any statement, any possible statement, even when low random process is modeled, and probability for a Bayesian is a way to represent an individual's degree of belief. So you may say, I think that if we run again the elections in Italy now, it's likely, it's 90% likely that the right party wins. This is your degree of belief. There is no way to prove it, because you need to run the election to make a check. Of course, you may make polls among the people, but polls may give an indication to you. Is a way to take into account some physical knowledge, but they can't give you the answer. You have to run the election if you want the answer. So this is a degree of belief. Even if it is based on polls, if you say that Berlusconi has 90% probability to win the next election if we have them now, this is your degree of belief. Other people may say no, I think it's not 90% but 60 or 30 is a degree of belief. This is easy. It's quite easy because you can assign a probability to every statement. Okay? And of course, degree of belief, one may say, I don't trust you. But on the other hand, degree of belief means that you can take your physical knowledge of the process into account. Any information, you can take any information into account. And if you are good in doing this, you are indeed capable of expressing a good judgment. So, for instance, you can generate a synthetic series because you may say, okay, let me start from the 1st of May. I think it's likely that the river flow takes this value. And you may do so because you look at the general rainfall in May, what is the rainfall series, how they behave in May, and you guess, based on your belief, a value that may be correct for river flow the 1st of May, and then you pass to the 2nd of May. If you have very good knowledge of the process, in doing so, you are able to generate a synthetic series that is quite correct. Okay, now let me pass to the first definition, which is more rigorous. And it's the frequentist definition. And in order to derive probability accordingly to the frequentist definition, you have to define an experiment. And so frequentist statisticians, they want to define an experiment. And therefore, they run the experiment and estimate probability. Let me give you a very simple example. Let's think to the example of tossing a coin. If I have a Bayesian, I take the coin, I look at it, I see that it's balanced, it's not loaded, which means unbalanced. You may have a coin where the center of gravity is not right in the center of the coin. But a Bayesian would take the coin and would just try to understand if there is some load, and if the Bayesian doesn't see any load, says, okay, the probability of getting an head is 50%. The frequentist would toss the coin 10 times, look at the results, and then would say, okay, I got 6 heads, so my guess is that the probability of getting an head is 50%. Because, of course, there is some uncertainty. If I got 6 heads, means that the probability probably is 50%. If they are good in doing that, they give the same result. But there is a huge difference. In the first case, the Bayesian just look at the coin, doesn't make an experiment. In the second case, the frequentist wants to make an experiment. And for instance, the experiment may be in hydrology to look at all the river flows that you observe in May. And then the frequentist look at the average value, the standard deviation, and is able to understand the probability for a given value of the river flow to occur in May. Because he looks at all the values and he considers any individual value as an experiment. Again, keep in mind that if they are correct, they give the same result. Good. And let me also say that in hydrology, usually, I would say that the frequentist approach is the classical approach, and the Bayesian one is becoming more and more popular today. This is just my consideration. Now, we need some more. So let's give a definition for probability. The definition helps us because either if we decide to adopt the Bayesian approach or the frequentist one, we need anyway to define what probability is. And there is a definition that was proposed by a famous Russian statistician called Kolmogorov in 1940, and he says basically he developed these 3 axioms, and these 3 axioms are the basis for the definition. So basically Kolmogorov stated that probability should satisfy all these 3 axioms, and any quantity, whatever defined, that satisfies these 3 axioms is fine to define probability. So now let's refer to, first of all, let's make clear that probability refers to an event, like a flood, like a drought, but usually we associate to this event a number because it's more handy for us. It's it's easier to treat. So we make an association. To the flood, we associate usually the river flow. And even to the drought, usually we associate the duration, which is important for us to quantify how much dangerous is a drought. And also we associate to the drought the river flow. And therefore we make an association between the event and the number. This association, this number that is associated to an event is called the random variable. So we usually speak about random variable. What is the random variable? It's an association between a random event and a number. And this number is the outcome of the event and can be real or integer. In the case of tossing a coin, it's just a binary variable, 0, 1, add and cross. And you can use 0, 1. In the case of river flow, it's a continuous variable. But now let's assume that we are dealing with variables that are discrete, not continuous. Okay, so it can be an integer variable, it can be a binary variable, discrete. Okay, so probability lies in the range 0, 1. You can express probability in percentage terms, as people usually do. It means that it varies between 0 and 100%. This is the first axiom. Second axiom. Probability of an event that is certain is 1. Probability of the impossible event is 0. Good. Third axiom. It's the additive property. The probability of getting either event 1, A here, sorry, or event B or event C is equal to the probability of A plus probability of B plus probability of C. I make the example again of tossing a coin. If you have 50% probability of getting an head and 50% probability of getting the cross, the probability of getting either head or cross is 50 to 50, 100%. Okay, which means probability of getting one or the other. So this symbology here means that the probability of getting A or B or C is equal to the sum of the individual probabilities. This is the additive property. Okay. Then, here there is a definition of random variable. And then you may have an engineeristic interpretation. So for you, it's the likelihood of an event, which varies between 0 and 1. But still, these axioms needs to be met. Okay? Then, let me see the next slide before I move forward. Yeah, okay. Now, the three axioms, again, these three axioms, lead to a very straightforward way to define the probability for a frequentist. I said frequentists want to define an experiment and run it. So I said we are dealing with discrete variables. So let's suppose that a frequentist runs 100 experiments. And let's suppose that this frequentist gets 20 events A. Then he will define the probability as the ratio of positive outcomes of A outcomes over the total. So basically he will say that the probability of A is given by n A divided by n, with n is the total number of experiments and NA is the total number in which you got an A outcome. This is the frequency of occurrence of A. So the frequency of occurrence is an estimate of probability for a frequentist. And so you can understand the meaning of the word frequentist. And you see that axiom 1 is satisfied. You won't get here a result that is lower than 0 and greater than 1. The second is of course satisfied if you look at this definition. And the third is again satisfied. So in the head-cross case, I toss the coin 100 times, I count the number of heads, and then I compute the probability as the ratio between the number of heads and the number of trials, 100. This is an obvious definition. And this is what is written here. Okay, and this is a consideration that I already did. So, in what follows, let's stick on this definition. Let's forget about the Bayesian definition in what follows, because we deal with numbers, we can define experiments, and so let's stick on this classical frequentist interpretation. And now let's again forget about Bayesian probability, and I just wanted to mention it because this is a term that you will find very often. Whatever you, in your career, in your future career, you will have to deal with probability, and it's very likely that you will have to do, then you will hear about Bayesian. And so now you know what it means. But so far the message that you can keep for this hour of lecture is we adopt a statistical representation. Statistical representation deals with uncertain processes, and therefore being the process uncertain, we need to look at the process in terms of probabilities. What are probabilities? Is you focus on an event and you try to understand its frequency of occurrence. This is what I said at the beginning. And this is exactly what you do by computing the probability of an event. So now, of course, our task is to try to understand, given that we want to generate river flows, is to try to understand their probability. And let me anticipate a complication, which is why applying probability in hydrology is not easy. Because so far, so good. You may say, this is very easy. This is very easy. And because, you know, I have a time series of observed data, I want to get a replica, so it's quite easy that I try to understand the frequency of occurrence of each value in the observed data, and I replicate it. So far, so good. But you see, if you try to think, how can I do that? Give me, for instance, if I give to you a series of 5 years of daily river flows, and I ask you, okay, this is definition, please estimate the probability of, and give me a means to obtain a synthetic river flow. Then you start thinking to it, and I think that you can easily identify two main problems. Two main problems. The first problem is that you look at your data, and you see that your data don't look like an add and cross problem. Don't you like tossing a coin? Don't like tossing a coin. Your data, you have different values, and each of them appears only once, because they are real data. So the first problem is, okay, I don't have a finite number of outcomes. The river flow is not just two outcomes, like flow or no flow. No, there are infinite outcomes, because the river flow is a real number. So you have infinite outcomes. So the first problem is, now, how can I identify the probability when I have an infinite number of possible outcomes? First problem. Second problem, you would say, okay, but there is a fundamental difference between tossing a coin and looking at river flows. And the difference is that tossing a coin, we are talking about an independent event. Independent means that if you toss once and you get an head, the second toss is not influenced by the outcome of the first one. So you start from scratch every time. This means that the events are independent. If you look at river flows, they are not independent. If you go on the banks of the Po River today and you look at the river flow and you go tomorrow, it's unlikely that tomorrow the Po River is dry. Because, of course, if today is very high, and today is, then you expect that tomorrow is still high. So it means that the outcome of your experiments, the outcomes of your experiment are not independent. So this is the second problem. So you have to take into account the past history of the process. You cannot just every day for the Po River toss coins. This is the second problem. And then, in the next, let's say, tomorrow and next hours, I will deal with this topic. We will have to learn how to solve these problems. So, keeping the memory of the process into account, first problem. Second, how to deal with infinite outcomes. Okay. Now let me concentrate on the second problem. Infinite outcomes, which means that the random variable is a real continuous variable. We need to modify the definition of probability to be able to assign to a real number, a real outcome of a continuous variable, a probability. Why that? Because, you know, if you apply this definition of probability, the frequentist one, and you count the number of outcomes for a real variable against the total, you get a value that is very close to 0, because a real variable occurs just once. If you make an experiment like milliard of times, billion in English, billion of times, and the outcome of the experiment is a real variable, which means that the number of digits is infinite, each outcome is unique. You won't get the same outcome for more than once, which means that the individual probability of each outcome is 0, close to 0. And therefore, of course, this is something that we need to change. We need to adopt a different definition. Okay, so what is this different definition? And this is a bit boring to introduce, we have to say. So here, let me keep this one, and let me turn to the real case. And this is your outcome for which you want to estimate the probability. This could be river flow, Q. And if it is a river flow, then it is bounded, lower bounded to 0. But still, you have infinite outcomes. So let's suppose that I want to estimate for this Q star what is the probability. Okay, so let me define an interval around Q which has an amplitude of delta Q. Okay, and then let me perform my experiment, which is very often just look at the series, at the time series of data, and let me count how many times my observed values, outcome of the process, fall into this interval. So basically, let me count the number of times in which you have, let me define the interval as 2 delta Q, just for simplifying the notation. The number of times in which you have the river flow Q, which is greater than Q star minus delta Q, and lower than Q star plus delta Q. Let me compute then this number, and let me divide this number by 2 delta Q. Let me compute the limit for delta Q tending to 0, and let me define this one as probability with lowercase p, of Q star. And this is not probability, but probability density. Okay, now this definition given in this way, and I think let me there is a number of experiments that must be introduced here. So let me put here the number of experiment n. So what happens here? First of all, this definition for probability density, I call it probability density because I want to make a difference. So I used probability for discrete variables, I use probability density for random variables. This definition, first of all, please note that the number that we derive is dimensional, which means that you see that here you have a number, here you have a number, and here you have a river flow, so it's dimensional. This definition, of course, gives to you a finite number because you have, for decreasing delta Q, you have the numerator that is tending to 0 and the denominator which is tending to 0. The relationship, the ratio among the two gives rise to a finite number. So it doesn't tend to 0. This number, if you bring delta Q close to 0. Now, basically, this is an indication of the probability for you to get individual values of this real variable, and it is very important to notice what happens if you take the integral of this quantity here. If you take the integral, so basically the integral I mean over a portion of the real axis which represents the domain of your real variable. So if I take, for instance, the integral between 0 and q prime, let's say that q prime is here, of p q star of q, let's say, in the q, so if you compute the integral of this probability density, again, over a piece of the domain of definition of the real variable, what you obtain, first of all, is a dimensionless number, because you compute by dq, and here, and therefore you compensate the dimension at the denominator. And what you get is called with capital P q prime, and basically is the probability of your variable to get values that are included here. So you turn it to a kind of discrete definition. You go back to the discrete definition. You compute the probability of your values to fall inside here. And this definition satisfies the axioms of probability. This cumulative probability, this is called cumulative probability. or some people just use probability, but the correct term is cumulative probability. This satisfies the definitions that I have shown to you before. The axioms, sorry. And again, this cumulative probability is the probability to get into here. Some people say the probability, but usually, let's distinguish. When we talk of real variable, we talked about probability density and cumulative probability. And the cumulative probability is analogous to the probability that we define for discrete variables, because it's without dimension and also satisfies the axioms. And be careful, there is another physical interpretation which is very important. This result is also called the probability of not exceedance of Q prime. Because of course, if you have the probability of your variable to fall within this range between 0 and Q prime, this is also the probability of not exceedance of Q prime. So basically you go over the river and you look at the river flow value today, and basically you compute the probability of not exceedance of this river flow value that you see today, for instance. So let me summarize, because I am conscious that I abused of your patience. So let me summarize. Discrete variables, probability, defined as the frequency of occurrence of each event. Continuous variable, probability density, defined in this way by referring to an infinitesimal interval. Integral of the probability density, which is the cumulative probability, which is also the probability of not exceedance and is analogous to the probability for discrete variables. So this is what we have to compute. If we want to simulate a time series, and we have solved the first problem, because I said the second, sorry. I said that the second problem was that we have infinite outcomes. Now, basically, we divided our real axis in sub-intervals, and we have a finite number of outcomes now, through this definition of probability density and its integral. Be careful, the probability density was this definition here, 1, and the integral is the cumulative probability. So when we have a real variable like river flow, what we have to estimate is either the probability density or the cumulative probability. By the way, this problem can be solved in R with just one line. And of course, now we have to understand how, by looking at a time series, we can estimate this cumulative or density of probability. They are analogous because one is the integral of the other. Now the question is, how can we identify this probability in the presence of memory of the system? Okay? Let me see. Yeah. Okay, good. Now, the problem is still there. As I said, we have to describe this function. So either we describe the probability density of Q, or the probability of Q. This is our problem. So either to describe the probability density or the cumulative probability. How can we do that? Allora, there is, sorry, allora is Italian. Then there is a solution in engineering, which is to estimate a function f equal fq. So to define a function of q which expresses the probability. And then of course you can estimate p, capital PQ, like the integral between, let's say 2 prime, 0 and 2 prime of fq in the q. We need this function f. That's our problem. And what is written here is analogous to what is written on the screen, because you see that there is written then this function, which is, okay, I use the capital F here, and the capital F to indicate the integral, and the lowercase f, like here, to indicate the function for the probability density. And so let's look at this expression here. It's the same that I have written there, with the only difference that here I put 0, and here in general there is a minus infinity, but I put 0 there because I refer to river flows. Of course,